Our topic now is looking into nonlinear programming and evolutionary optimization. So a nonlinear programming problem has a nonlinear objective function and or one or more nonlinear constraints. These problems are formulated and implemented in virtually the same way as linear problems. But the math involved in solving nonlinear programming problems is quite different than for linear programming problems. Solver tends to mask this difference, but it's important to understand some of the challenges that could be encountered when solving for nonlinear programming problems. So, unlike linear programming problems where every constraint can be expressed as a straight line, we find that that is not necessarily the case. So the feasible region can take a variety of shapes, and so can the objective function. It can be a circle, it can have a curve to it. The objective function might be linear, but then the constraints might not be, so you end up with a funky shaped feasible region but a straight objective function. In other cases, you may end up with a nonlinear objective function but linear constraints, and all varieties in between. So to solve nonlinear programming problems, Solver uses the Generalized Reduced Gradient Algorithm, or the GRG nonlinear approach. We can also use the GRG approach on linear programming problems, but it's slower than the simplex method. Although for most problems that you're solving, it is probably not too difficult to use the GRG method, even though it takes longer, because a lot of problems that we're working with aren't terribly complex, at least in this class. But in reality, problems can get very complex, so it is important to choose the right method. So the following few slides give a general but somewhat imprecise idea of how GRG works. So we can run into some challenges when we're trying to attempt to solve nonlinear programming problems. In this case here, we see that the feasible region takes this rounded shape. So we can try to use level curves to find our optimal value, and we see that when we go from A, our starting point, to that first line in B, and then from B to C, the arrows start curving over, which indicate that this is a nonlinear problem. Although we can probably conclude that where E meets the feasible region is probably ideal. But in nonlinear problems, the feasible region may also take a shape like this, where there is more than one optimal solution, where there is a local optimal solution and as well as a solution that is local and globally optimal. So in this case, where C meets the feasible region is a local optimal solution, and then the feasible region retreats, and that level curve actually goes back into the feasible region, and point G is both the local and global optimal solution. So it is the best solution overall, but it is also the best solution on that sort of bulge out in the feasible region. So in the graphic on the left-hand side, the feasible region is convex, so all lines connecting 2 points in the feasible region fall entirely within the feasible region. But the other one is non-convex, so not all lines connecting 2 points in the feasible region fall entirely within the feasible region. Convex problems are much easier to solve than non-convex problems. This graphic sort of illustrates what a non-convex problem can look like, where you've got multiple local optimal values, and it is just a real challenge to solve. And it can take a lot of time and computing power to solve these problems. But what we can take away from nonlinear programming algorithms is that it's not always best to move in the direction producing the fastest rate of improvement in the objective, and that nonlinear programming algorithms can terminate at local optimal solutions, and the starting point influences the local optimal solution obtained. So when we're choosing our starting point, we want to avoid the null starting point, and when possible, we want to use starting values of approximately the same magnitude of the expected optimal values. Something to consider is that when solving a nonlinear programming problem, solver normally stops when the first of 3 numerical tests is satisfied, causing one of the following 3 completion messages to occur. Solver found a solution, all constraints and optimality conditions are satisfied. So this means that solver found a local optimal solution, but does not guarantee the solution is the global optimum solution. Another completion message is that solver is converged to the current solution, all constraints are satisfied. And this means that the objective function value changed very slowly for the last few iterations that solver worked through to arrive at that output. And finally, solver cannot improve the current solution, all constraints are satisfied. And this rare message means your model is degenerate and the solver is cycling. And degeneracy can often be eliminated by removing redundant constraints in a model. So earlier in the class, we talked about redundant constraints and how they're redundant because they don't form any boundaries on the feasible region. And it may not have seemed like a big deal before to include them in the model, but when you run into this message, you really want to evaluate whether or not you have redundant constraints, and that's the easiest way to solve this problem. So let's look at an example. Let's look at the economic order quantity problem. It's one of the most common business problems for which nonlinear optimization can be used. This problem is encountered when a manager must determine the optimal number of units of a product to purchase whenever an order is placed. The basic model for an EOQ problem assumes 1. Demand for or use of the product is fairly constant throughout the year, and 2. Each new order is delivered in full when the inventory level reaches 0. Keeping in mind that small orders result in low inventory levels and carrying costs, as well as frequent orders and higher ordering costs, and large orders can result in higher inventory levels and carrying costs, but less frequent orders. So this figure illustrates the inventory patterns observed for a product when the preceding conditions are met. In each graph, the inventory levels are depleted at a constant rate, representing constant demand. Also, the inventory levels are replenished instantly whenever the inventory levels reach 0. The key issue in an EOQ problem is to determine the optimal quality to order, or the optimal quantity to order whenever an order is placed for an item. The trade-offs in this decision are evident in the graphs, indicating 2 ways of obtaining 150 units of a product during the year. In the first graph, an order for 50 units is received whenever the inventory level drops to 0, and this requires 3 purchase orders to be issued during the year and yields an average inventory level of 25 units. In the second graph, an order for 25 units is received when inventory levels drop to 0. This requires that 6 purchase orders be issued throughout the year and results in an average inventory level of 12.5 units. Thus, the first ordering strategy results in fewer purchase orders and lower ordering costs, but higher inventory levels and higher carrying costs. Conversely, the second ordering strategy results in more purchase orders and higher ordering costs, but lower levels of inventory and lower carrying costs. In the basic EOQ model, the total annual cost of stocking a product is computed as the sum of the actual purchase cost of the product plus the fixed cost of placing orders plus the cost of holding or carrying the product in inventory. The first term in this formula DC, represents the cost of purchasing a year's worth of the product. The second term, D over Q times S, represents the annual ordering costs. Specifically, D over Q represents the number of orders placed during a year. Multiplying this quantity by S represents the cost of placing these orders. The third term, Q over 2 times CI, represents the annual cost of holding inventory. On average, Q over 2 units are held in inventory throughout the year. Multiplying this term by CI represents the cost of holding these units. And this figure shows the relationships among order quantity, carrying cost, ordering cost, and total cost. Notice that as order quantity increases, ordering costs decrease and carrying costs increase. The goal in this type of problem is to find the EOQ that minimizes the total cost. Let's look at an example. Alan Wang is responsible for purchasing the paper used in all of the copy machines and laser printers at the corporate headquarters of MetroBank. Alan projects that in the coming year, he will need to purchase a total of 24,000 boxes of paper, which will be used at a fairly steady rate throughout the year. Each box of paper costs $35. Alan estimates that it costs $50 each time an order is placed, and this includes the cost of placing the order plus the related costs in shipping and receiving. MetroBank assigns a cost of 18% to funds allocated to supplies and inventories because such funds are the lifeline of the bank and could be lent out to credit card customers who are willing to pay this rate on money borrowed from the bank. Alan has been placing paper orders once a quarter, but he wants to determine if another ordering pattern would be better. He wants to determine the most economical order quantity to use in purchasing the paper. This is the model we're looking at. We're trying to minimize the equation shown, and the value for Q must be greater than or equal to 1. So let's look at how we would go about setting this up in Excel. The image on this slide diagrams how you would set this up in Excel, as well as the key cell formulas that are necessary to make this model work. And then this diagram illustrates the solver settings. The goal in this problem is to determine the order quantity, the value of Q, that minimizes the total cost. That is, we want solver to determine the value for cell D9 that minimizes the value in cell D14. Let's take a look in Excel. So this is the MetroBank model. Annual demand is for 24,000 boxes of paper. The cost per unit is $35. The cost per order is $50, and there's a holding cost of 18%. Our order quantity is our decision variable, so solver will change that for us. D5 times D4 is our purchasing cost, so that's the annual demand and the cost per unit. The cost of ordering is D4 over D9 times D6, so the annual demand divided by the order quantity times the cost per order. Inventory cost is calculated as the order quantity divided by 2 times the holding cost percentage times the cost per unit, and then total cost, which is our objective cell, is the sum of D11 through D13, which are the different costs that are involved that in their sum would indicate the minimized total cost. So let's take a look at solver. We'll go over to data and solver. So our objective cell is D14. We want to minimize this value by changing variable cell D9, and D9 must be greater than or equal to 1. We want to use the GRG nonlinear approach here. Instead of using simplex, we want to use GRG nonlinear. And we find that the ideal order quantity is 617.21. And that may be problematic, though, because the value is not an integer, so you may need to investigate that further. But that's one way that we could approach this problem. So the setup is fairly straightforward. And what this basically, by setting this constraint where D9 is greater than or equal to 1, it ensures that there is at least one order placed per year. So that's the EOQ model in Excel. Let's go back to our slide deck. We have more fun examples coming up. So there's another way to determine the optimal order quantity using the simple EOQ model. Using calculus, it can be shown that the optimal value of Q is represented by the square root of 2ds divided by Ci. So we find, using calculus, that we end up with the same result. So the value obtained here is almost the same value obtained using solver. The slight difference in the results might be due to rounding or solver stopping just short of converging on the exact solution. Although the previous EOQ formula has its uses, we must often impose financial or storage space restrictions when determining optimal order quantities. The previous formula does not explicitly allow for such restrictions, but it's easy to impose these types of restrictions using solver. That's one of the reasons why we like using solver. Moving on, many decision problems involve determining optimal locations for facilities or service centers, like manufacturing plants, warehouses, fire stations, ambulance centers, and yes, hospitals. These problems usually involve distance measures in the objectives, in the objective cell and or the constraints. So this type of calculation is likely to be involved in any problem in which the decision variables represent possible locations. The distance measure might occur in the objective function. For example, we might want to minimize the distance between two or more points, or it might occur in a constraint. For example, we might want to ensure that some minimum distance exists between two or more locations. Problems involving this type of distance measure are nonlinear. And the straight line or Euclidean distance between 2 points, so x1 and y1, is calculated using this distance equation. And this equation also comes up in data mining when you're trying to find and group observations based on their distance to each other, but it also comes up in location problems. So you will see Euclidean distance again. So let's take a look at a location problem. The Rappaport Communications Company provides cell phone service in several Midwestern states. The company is planning to expand its customer base by offering cell service in northeastern Ohio to the cities of Cleveland, Akron, Canton, and Youngstown. The company will install the hardware necessary to service customers in each city based on pre-existing communication towers in each city. The new tower will have a 40-mile transmission radius. So here the company needs to construct a new communications tower somewhere between these cities to handle intercity calls. This tower will also allow cellular calls to be routed onto the satellite system for worldwide calling service. The tower the company is planning to build can cover areas within a 40-mile radius. Thus, the tower needs to be located within 40 miles of each of these cities. And the scale of this graph is miles. But you may also be working with GPS coordinates. So when you're working with GPS coordinates and you want to put a distance constraint, make sure that you translate that constraint into degrees and you do not use miles. You need to work with the same units. So it's important to note that we could have overlaid the x and y axes on a map in more than one way. The origin could be located anywhere on the map without affecting the analysis. To establish the xy coordinates, we need an absolute reference point for the origin, but virtually any point on the map could be selected as the origin. We can also express the scaling of the x-axis and the y-axis in a number of ways: meters, miles, inches, feet, and so on. For our purposes, we'll assume each unit along the x and y axes represents 1 mile, but again, you might be working with GPS coordinates, in which case you're looking at degrees. So let's define the decision variables. Definite xy coordinates have been established to describe the locations of the cities. These points are fixed, but not under the decision maker's control. But the coordinates of the new communications tower have not been established. We'll assume that Rappaport wants to determine the tower location, minimizing the total distance between the new tower and those in each of the 4 cities. And note that this is equivalent to minimizing average distance as well, as the coordinates of the new tower represent the decision variables in this problem, which are defined as x1, the location of the new tower with respect to the x-axis, and y1, location of the new tower with respect to the y-axis. Next, we define our objective function. And the objective in this problem is to minimize the total distance from the new tower to each of the existing towers, defined as the equation on this slide, where the Euclidean distance between the different towers is minimized. The first term in the objective calculates the distance from the tower in Cleveland at xy coordinates 5 and 45 to the tower to the location of the new tower, whose location is defined by the values x1 and y1. The remaining terms perform similar calculations for the towers in Akron, Canton, and Youngstown. So let's take a look at our constraints. The problem statement noted that the new tower has a 40-mile transmission radius and therefore must be located within 40 miles of each of the existing towers. The following constraints ensure that the distance from each of the existing towers to the new tower is no larger than 40 miles. Graphically, these constraints would be drawn as 4 circles, each with a 40-mile radius, each centered at one of the 4 existing tower locations. The intersection of these circles would represent the feasible region for the problem. So in Excel, we would set this up with 4 rows for each of our towers, as well as a row for our new tower coordinates, which are our variable cells at the very top. Our objective cell is trying to minimize the distance, and then our constraints are that distance between the different towers. So let's take a look in Excel. So here we find our decision variables, or our variable cells. These have no formula in them because Solver will adjust them. To look at our distance to each tower, we have a formula that takes the square root of C7, which is the x coordinate for the Cleveland Tower, minus the new coordinate for the new x coordinate for the tower, squared, plus D7, which is the y coordinate for Cleveland, minus the new coordinate for the new y coordinate for the new tower squared. So this equation is copied down the next 3 rows. And this constraint is that these values must be small. The values in column E here that are highlighted in red, these are our constraints, and they must be less than 40 because we're working in the scale of mileage. So let's go to data and solver. So here we want our objective cell to be cell E11, and we are trying to minimize the distance by changing variable cells C6 and D6, subject to the constraints, where the cells in column E must be less than or equal to those in column F, which are equal to 40. If there's no maximum allowed value, if there's not a specific distance that you are looking for, you just want to minimize the values in column E. You don't need to worry about having the maximum allowed value in column F. But we'll add this constraint. This is nonlinear, so we'll run it as a GRG nonlinear problem. And it is recommending this, basically putting the tower right on top of the Akron tower. So we might want to rethink that or adjust some of our settings, but in this case, that's the minimum value for E11, which is just the sum of E7 to E10. And you can see that the distance is 0 from Akron. So basically it's saying put a second tower in Akron. So, and this is the solver settings for that problem. And the solution indicates that if the new tower is located at the coordinates x1 equal to 12 and y1 equal to 21, the total distance between the towers is about 81 miles. The average distance is about 20.4 miles. If you try resolving this problem from a variety of starting points, you can verify this is the global optimal solution to the problem. Interestingly, the coordinates of this location for the new tower are virtually identical to the coordinates of the existing tower in Akron. So the solution to this problem may not involve building a new tower at all, but instead Rappaport may want to investigate the feasibility of upgrading or retrofitting the existing Akron tower to play the role of the, quote, new tower, unquote. So where should we locate the new tower if we want the maximum distance to the existing towers to be minimized? So now we want to minimize the maximum distance from a tower, because we saw in the previous example that our distance from one of the towers was really pushing the limits in terms of overall distance. So now we're looking at maximum values for cells E7 through E10, and we're not as worried about minimizing the total, we're worried about minimizing the maximum distance. So pay attention to that difference. In this, the first example would relate to the first scenario in the hospital siting homework. This would relate to the second scenario where you're minimizing the maximum distance from any one of the 4 towers. So we would go into solver And we wouldn't change any of the constraints, but we would change the objective cell, in this case to E12. And we're trying to minimize this maximum distance. And we'll click solve. Took us back to our previous example. Here we have the updated coordinates where we're minimizing. This is the second example, the second Rappaport communications example, and here we see the X and Y coordinates are a little bit different, and the distance from any given tower is reduced, although it's still closest to the Akron tower. Just something to keep in mind. And that sums up examples of location problems. So that's just a diagram of what it looks like in Excel with the key equations involved. You can see for E12, there is a new equation, and that is the maximum of E7 through E10. When solving location problems, it's possible that the location indicated by the optimal solution may simply not work. For instance, the land at the optimal location might not be for sale. The land at this location might be a lake. The land might be zoned for residential purposes only, etc. However, solutions to location problems often give decision makers a good idea about where to start looking for suitable property to acquire for the problem at hand. It might also be possible to add constraints to location problems that eliminate certain areas from consideration if they are inappropriate or unavoidable. Now let's look at a network flow problem. Safety Trans is a trucking company that specializes in transporting valuable and hazardous material. Due to the nature of its business, the company places great importance on maintaining a clean driving safety record. This helps keep their reputation up and keeps insurance premiums down. Furthermore, the environmental consequences of even a minor accident could be disastrous. Most trucking companies are interested in routes providing the quickest or least costly transportation, but Safety Trans likes to ensure it selects routes least likely to result in an accident. The company maintains a database of highway accident data, which it uses to determine the safest route. And the company is currently trying to identify the safest routes for carrying a load of hazardous materials from Los Angeles, California to Amarillo, Texas. And this is what the network looks like for this problem. And the numbers on the arcs, which are the links between the different nodes, and each node is a city, represent the probability of an accident occurring. Safety Trans maintains a national database of the probabilities of crashes occurring developed from data they receive from state and federal departments of transportation. Also note that at Los Angeles you see a -1 because that's where we're shipping from, and we want it to arrive in Amarillo where it's +1. So let's define our decision variables. So for each value of y, it's equal to 1 if the route from node I to node J is selected and 0 otherwise. So we need one variable for each arc or route in the problem. Each decision variable indicates whether or not a particular route is used. The specification for each of these variables is as illustrated on the slide. So let's define our objective. The aim of this problem is to find the route minimizing the probability of a crash. Pij is the probability of a crash traveling from node I to node J. Then the probability of not having an accident when traveling from I to J is 1 minus Pij. For example, the probability of not having a crash between Los Angeles and Las Vegas is 1 minus 0.003, which equals 0.997. Let's take a look at our constraints. So we have our flow constraints. To solve a shortest path network flow problem, we assign the starting node a supply value of -1. and assign the ending node a demand value of +1 and apply the balance of flow rule. The first constraint ensures that 1 unit flows out of node 1 to nodes 2, 3, or 4, and the last constraint ensures that 1 unit flows into node 10 from nodes 7, 8, or 9. The remaining constraints ensure that any flow into nodes 2 through 9 is balanced by an equal amount of flow out of those nodes. And this diagram illustrates the setup in Excel. And we can see it here. So we have all of our different arcs, so all of the different possible combinations of links in the route, as well as information on our nodes. Our variable cells are whether or not it's selected, and they are in column A here. Our objective cell is the probability of a safe trip, which is the product of G6 through G23. So here our probability of no crash. And then our constraints are indicated here for the inflow and the outflow for each of the nodes. And here we see the supply is -1 in Los Angeles and demand is equal to 1 in Amarillo. So this slide illustrates the settings in Solver that we want to use to approach this problem. So our objective cell is going to be G24, and we're trying to maximize this value. We want the probability of a safe trip to be really high, and we do this by changing variables A6 through A23, and we've got 2 constraints to add. The first constraint is that K6 through K15 has to be equal to the value in column L, and our values in A6 through A23 must be binary, because you either choose the link or you don't choose the link. We click OK. We use the standard GRG nonlinear engine. And we hit solve. And we find here that the probability of a safe trip is 99%. And we go from Los Angeles to Phoenix, Phoenix to Flagstaff, Flagstaff to Albuquerque, and Albuquerque to Amarillo. So isn't that cool? And here we see that our inflow and outflow constraints are all met, and we're going to have a really safe trip. So I think that's pretty cool. And the second tab just shows you, again, the results of using Solver for that model. And it also includes the Solver setup in case you need to refer to it. So small differences in probabilities can mean really big differences in expected values, and we find that the expected value is substantially different between a 99% chance of a safe trip and a 96.26% chance of having a safe trip. So this type of problem is also useful in reliability network problems, so finding the weakest link or path in a production system or telecommunications network. On to our next problem. A few weeks ago, we looked at a project selection example in which we wanted to select the combination of projects that produced the greatest net present value, or NPV, subject to various resource restrictions. In these problems, there's often some uncertainty about whether a selected project can actually be completed successfully, and this success might be influenced by the amount of resources devoted to the project. The current example illustrates how NLP techniques can be used to help model this uncertainty in a selected project's potential for success. C-suite directors at TMC are figuring out how to allocate their R&D budget for next year. 6 projects are under consideration. The directors believe the success of each project depends, in part, on the number of engineers assigned. Each project proposal includes an estimate of the probability of success as a function of the number of engineers assigned. The table summarizes initial startup funds necessary for each project and the estimated NPV the project will generate if successful. This is the probability of success for selected projects in the TMC problem. TMC's directors agreed to hire up to 25 engineers to assign to these projects and are willing to allocate $1.7 million of the R&D budget to cover startup costs for selected projects. They must pursue the project selection and resource allocation strategy, maximizing the expected NPV. TMC's directors make 2 separate but related decisions. They must determine which projects to select, which we can model from with a set of binary variables, and they must also determine the number of engineers to assign to each project, which will be represented by the letter X. So TMC's directors want to maximize expected NPV, so the objective function must correspond to this quantity. This requires multiplying each project's expected return by the probability of the project being successful. So we have a number of constraints to apply to this problem. The selected projects in total may not equal more than $1.7 million in startup funds. No more than 25 are required. No more than 25 engineers are required across all selected projects. And engineers can only be assigned to selected projects. In the linking constraint, we ensure X can only be greater than 1 if Y is selected. Or instead of the previous set of constraints on the number of engineers, we could just use the single nonlinear constraint, the 4th equation on the slide. However, when given the choice between linear and nonlinear constraints, for ease of replication and calculation, always go linear. So this slide illustrates the setup of the TMC problem, which is shown in Excel on the screen. So our variable cells are B7 through C12. Column B is binary, it's whether or not we select the project, and C is the number of engineers assigned. The constraint here in cell C13 is the total number of engineers used. The linking constraint is structured so that engineers are only assigned to projects that are selected. Probability of success is a function of the number of engineers assigned and the probability. Column G is the NPV if successful. The expected NPV is the probability of success multiplied by the NPV, and the startup cost for each project is listed here. This value is the constraint on expenditures, so we cannot spend more than $1.7 million. And then H13 is our objective cell. That is the total amount of money we're willing and able to spend. So this slide is an overview of the settings required in Solver to address this model. So let's go to Solver. Our objective cell is H13. We want to maximize the expected NPV, so we're going to leave that as maximized. We're going to change cells B7 through C12, and that's subject to a few constraints. C13 has to be less than or equal to C14. The startup cost of I13 has to be less than or equal to $1.7 million. D7 through D12 are linking constraints. These are going to be less than 0. C7 through C12 has to be greater than or equal to 0. We cannot have a negative number of engineers. And then B7 through B12 has to be binary. And C7 through C12 has to take an integer value because we also cannot subdivide engineers. So those are our constraints for using the GRG nonlinear approach. And let's solve this problem and see what it suggests. This one takes a little bit longer to run. And I will note that if you adjust some of the values a bit, you may end up getting solutions that don't make a lot of sense. There are some limitations to what Solver can do with the given constraints. So we ran Solver, and we found that we can spend $1.65 million in startup costs to get $1.757 million in expected NPV by selecting projects 1, 3, 4, and 5. And note that those projects that were not selected do not have engineers on them. So that is perfect. The probability of success looks pretty good for all of these projects except maybe project 4. But on the other hand, project 4 is our least expensive project, so that's probably going to be okay and we shouldn't worry too much about it. And if you go to the TMC with Solver, you will see, you can actually see the whole problem set up and you can kind of dissect it and play around with it a little bit. So it's not necessary to always write out the algebraic formulation of an optimization problem. Although for your first 2 assignments, you did, because it's good for you. It ensures a deep understanding of the problem as well as how to structure linear and nonlinear programming problems in general. Solver can be used to optimize a number of pre-existing spreadsheet models that are inherently nonlinear. So a very famous application of nonlinear programming involves determining the best mix of investments to hold in a portfolio as to minimize financial risk. So Ray, an independent financial advisor, recently met with a new client, Paula, who wanted Ray's advice on how to best diversify a portion of her investments. Paula has invested a good portion of her retirement savings in the stock of International Business Corporation, or IBC, during the past 12 years. This stock has yielded an average annual return of 7.64% with a variance of about 0.0026. However, Paula wants to earn more on her investments, but is very cautious and doesn't like to take risks. Paula asked Ray to recommend a portfolio of investments that would provide at least a 12% average return with as little additional risk as possible. Ray identified 2 additional stocks from the National Motor Corporation, NMC, and the National Broadcasting System, NBS, that he believes could help meet Paula's investment objectives. Ray's research is summarized on this slide. So, defining our decision variables, we must determine the percentage of the total funds invested should go towards the purchase of each of the 3 stocks. So we need these 3 decision variables because these variables represent proportions We also need to ensure that they assume values no less than 0 and they sum to 1, which represents 100%. The objective in this problem is to minimize the risk of the portfolio as measured by its variance. In general, the variance of a portfolio consisting of n investments is defined in most finance texts as presented on the slide. Only two main constraints apply to this problem. We need a constraint to ensure the expected return of the entire portfolio achieves or exceeds the desired return of 12%. And because only 3 investments are under consideration for this portfolio, and our decision variables represent the percentage of funds invested in each of these investments, we must ensure that our decision variables sum to 100%. So let's take a look at how we could structure this problem. So this is just the portfolio data set up in Excel, and there are some equations that we need to consider to evaluate the different components of the portfolio. So we want to calculate the average annual return. So for IBC, that's 7.64%, and then also the covariance between the different investment options. And then here we add a few more cells that we can use as our objective variable and constraint cells. So our constraints are the expected return in the portfolio. The objective cell is the portfolio variance, which we want to minimize. And the variable cells are the percentage of the portfolio that we want to dedicate to each of the 3 different companies. So this is the proportion of the portfolio we would want to dedicate to each of the 3 companies. This is the total, which would be constrained to 1, representing 100%. The required return is 12%. And then this is our portfolio variance, which is our objective cell that we're trying to minimize. So let's open up Solver. So here our objective cell is going to be H16. It's our portfolio variance by changing cells G11 here through I11. And we need the value in H13 here to be larger or equal to our required return, and we want to minimize the portfolio variance. And then J11 must be equal to 1, the sum total of the proportion of the portfolio dedicated to each of the companies. We hit solve. So we see that about 27% should go towards IBC, 63% to NMC, and about 9% to NBS to get that 12% return that we're looking for. And this is the solver setup. And what's fun about this result is that it finds a portfolio that produces a higher expected return for Paula with less risk than was involved in her original portfolio. So in terms of portfolio theory, her original investment would be called inefficient. So there are 2 different conflicting objectives that can be applied to portfolio selection problems: minimizing risk, or portfolio variance, and maximizing expected returns. And we can apply this concept to portfolio optimization in the problem that we've been working on. So we can go back to the Excel sheet. And here we've added constraints to address risk aversion. So if you are extremely risk averse, this value would be 1. or 0 if you're not risk averse at all. So here you can get an expected return of almost 15% if you are not risk averse at all. But if we change that aversion value to 0.5, and note that the objective cell is now changed down a couple rows. And now we find that the portfolio variance is quite a bit smaller with the risk aversion value being increased to 0.5. So that's a handy tool when you're trying to figure out investments. You may be interested in a portfolio selection model when deciding what kinds of physicians to hire or what types of services to offer from a healthcare facility, for example. So this has a lot of applications in the healthcare field. So check out those examples. And then just a quick note on evolutionary algorithms. They're a technique of heuristic mathematical optimization based on Darwin's theory of evolution. And they can be used on any spreadsheet model, including those with if and or lookup functions in them, whereas some linear and nonlinear programming problems will not run with these functions in them. Evolutionary algorithms are also known as genetic algorithms. So genetic algorithms start with a set of chromosomes or numeric vectors representing possible solutions to an optimization problem. The individual components or numeric values within a chromosome are referred to as genes, and new chromosomes are created by crossover and mutation. Crossover is the probabilistic exchange of values between solution vectors, while mutation is the random replacement of values in a solution vector. Chromosomes are then evaluated according to a fitness or objective function, with the fittest surviving into the next generation. The result is a gene pool that evolves over time or iterations to produce better and better solutions to a problem. Solver's evolutionary algorithm picks up where its nonlinear GRG algorithm leaves off. As we've seen for nonlinear problems, the solution Solver generates depends on the starting point and may be a local rather than global optimal solution. Solver also tends to have difficulty solving problems with discontinuities and unsmooth landscapes, which are typical of spreadsheet models employing logical, like if, functions, or lookup tables. Although the evolutionary algorithm cannot completely avoid the possibility of becoming trapped at a local optimal solution, its use of a randomized initial gene pool and probabilistic crossover and mutation operators make this occurrence less likely. The evolutionary algorithm can operate on virtually any spreadsheet model. So, any of the examples we've looked at can be approached with the evolutionary model. So if the GRG nonlinear solution doesn't seem to make sense, or there are a lot of special conditions within your model, you can go ahead and use the evolutionary approach, which is the third option in the drop-down menu in the Solver dialog box, in addition to Simplex LP and GRG nonlinear. Well, I don't know about you, but I'm exhausted. So let's call it here. Good luck on the homework, and I'll catch you next time.